Okay, problem number 2 under crack stage topic. So we have here a example for doubly reinforced beam. So doubly reinforced simply means that you have a reinforced steel on the compression, both on the tension and compression side. Right, for problem number 2, we are required to compute the bending stress in the beam, of course in megapascal, for the beam shown, or the doubly reinforced beam, by using transform area method. Take note, this is crack stage. Okay, so F prime C 20.7 megapascal, N the modular ratio, that is 10, which is given on the problem, so no need for us to compute. And we have the moment on this beam, which is 100 kilonewton meter. Right? So this is the figure, or this is the beam, as you can see here. On the compression side, we have two 28 mm steel bar, and then on the tension side, we have three 28 mm steel bar. Right? Using transform area method, so we're going to transform the steel bars into an equivalent area of concrete. So as you can see here, this is the transform area. So on the singly reinforced beam, on the problem number 1, okay, for the steel sa may tension side, we have a transform area which is equal to N, okay, times AS, or area of the steel. Okay, so the new term here, or the new formula that we're going to use here, if this is a doubly reinforced beam, yung steel na meron sa compression side will have a formula of 2N minus 1 times AS. So, why 2? Okay, why 2N? So, according to the theory, okay, behind this, that the compression steel in the long run will be stressed twice, okay, as that of the tension steel. So, magiging 2N siya. Ang tanong, bakit may minus 1? Okay, minus 1 because this is, in this compression side, meron pang area ng concrete. So, as we all know, na itong steel na to, or on this side, is butas ang concrete, no? There's a hole on the concrete, but we are considering the whole area of the concrete here. Ayan sa transform area. Consider natin yung whole concrete, but ima-minus natin ngayon yung area sa may steel. So, meron siyang minus 1. Okay? To compensate dun sa area, dun sa butas sana na meron sa concrete. Okay? So, as you can see here, we need to compute the NAS and the 2N minus 1 AS for the transform area. And then, the height of our concrete, okay, will be unknown, so X. And then, the neutral axis, of course, is at the bottom of that concrete area. Okay, so this will be the dimension. So, from the neutral axis to the tension steel, 275 minus X. And then from the neutral axis to that of the centroid of the compression steel is X minus 7.5. So, pagka compression steel, usually meron siyang prime, no? AS prime pagka compression steel. Pag AS lang, tension steel ang kino-consider dyan, no? So, NAS, so N is 10, AS, area sa tension steel, is tatlong bar na 28 mm diameter. So, we have 5880 pi will be the answer for NAS. And then for the compression bar, transform natin, 2n minus 1. So, 2 times 10, that's 20 minus 1. So, 90 times dalawang 28 mm. So, times yung area ng isang 28 mm, which have an answer of 7,448 pi. Then, now, we proceed in solving the value of x, or determining the location of our neutral axis. So, that is like we solve dun sa problem number 1. So, it is the moment of the area about the neutral axis of the compression bar, compression side is equal to that of the tension side. So, we have here the area of the concrete, 250 times x, times the moment arm from the centroid of that concrete to that of the neutral axis, x over 2, plus dun tayo sa compression bar, ito yung area nya, and this will be the moment arm, which is equal to the area of the tension bar times the moment arm of the tension bar, okay, from that of the neutral axis. So we will have an answer class of 120.143 mm. Okay, so we already know the compression height. So next is we proceed to the moment of inertia of the transform area. We have here, it is the summation of I plus AD squared. Okay, so we have here 3 areas. Okay, area of the concrete, area of the tension steel, and area of the compression steel. So we have here I1 for the concrete. So for the I1, we have base 250 times height, which is the x, 120.143 cube all over 12, plus the area of that concrete. So that is 250 times 120. We will have this value here, and then we have x over 2, which is 60.0715 square. So we will have here a moment of inertia of that concrete, right? The next is I2, which is the moment of inertia of the compression steel. So we have 7,448 for the area, and then for the D we have 45.143 square. Okay, so that result to this value 476,83746.95 millimeter raised to 4, and of course that is the same with the I3. Okay, the methods area times D square. So we have here the value. So this adding all the moment of inertia, we have here the total moment of inertia 635,184,019 millimeter raised to 4. Okay, next is the bending stress. So this is the required. We have 3 bending stress for the concrete, stress for the tension steel, and stress for the compression steel. Okay, let's go first dun sa stress concrete. So we have M, which is 100 times 1,000 square para maging Newton mm, times YC, okay, from neutral axis to the extreme tension, compression fiber, 120.143 divided by I, we will have 18.91 megapascal. So next is the Fs for the steel. So we have N times MYS all over I. So we'll have these values here, and the answer is 43.80 megapascal. And the next is for the stress at the compression bar, Fs prime, we have, so here instead of N only, dahil 2N yung minultiply natin sa transform area, 2N pa rin yung multiply natin sa stress. So we have 2N MYS all over I. So we'll have this value here, okay, that is equal to 142.14. So the answer is For the bending stresses, we have the 3 bending stresses for the 3 areas on our beam. So that's how we solve doubly reinforced beam.